I'm Mr. Taru. In the next couple of videos, and again, I am doing pre-calculus, remember? So in the next couple of videos, we're going to touch on the concept of parametric equations. Now, these equations have a lot of applications in physics and in calculus. We are just going to be looking at the basic structure of parametric equations, do a video, this video, on examples of how to graph parametric equations, another video on how to bring two parametric equations back in together to be a single rectangular form equation, a regular function, and then we'll split some functions apart in a third video and make some parametric equations. So what you do here with parametric equations is it's actually a pair of equations, and we're going to describe the horizontal and vertical movement of an object in terms of time. So we're going to be describing x and y coordinates, where x has got its own function describing that horizontal movement, y has its own function of g of t, and then our variable of interest, our parameter of time. So again, especially in calculus and in physics, you would be able to therefore track just the horizontal movement of an object, maybe find the horizontal speed or acceleration at a given period of time, and do that as well with the vertical motion of your object separately, which really, again, has some very nice applications for physics and calculus. In this video, though, we're just going to learn how to do some basic graphs, effectively just using a t-table. You might want to call it a W table because we have three columns, one for t, one for x, and one for y. So to graph a plane curve where your functions are in parametric form, choose values of t. And we're going to do the values of t from low to high, so we're in increasing order. Substitute each value of t into the parametric equation to compute the value of x, and then separately to evaluate or compute the value of y. And then you're going to plot those points, again, I'm going to repeat myself here, in increasing order of t. Now, we're not going to just draw the graph, but since we're tracking the horizontal movement and the vertical movement separately based on time, we'll be able to, with some arrows, we want to indicate what direction the object is moving as opposed to just the path in which it follows. And those arrows, that motion is not always going to be left to right like we normally just read a function equation or function graph. So when we plot those points, we want to make sure that we do it from the t values going from low to high, and pay attention to the way that you're putting those points on your xy graph so that you can tell what direction the object is moving, as well as just simply what is the path. So let's get some of those examples done. Woo! Right. So our first example here, we got x equals t plus 3, y equals negative t squared. And we're going to do this for we mentioned that those directions said that sometimes the t value can be, enclosed within an interval of time. So here, we're only interested in t values between negative 2 and positive 2. So we're going to go negative 2, negative 1, 0, 1, and 2. Especially in pre-calculus, when we're only just touching on the ideas of parametric equations, please do not look at these and immediately go, okay, that's got a square term in it, it's probably going to be a parabola. Because, and this one will be, but that's only because we have a basic linear function for x. You can be really shocked by what the final version of these graphs look like. So make sure that you do take the time to do these t-tables, or W table if you will, I'm going to just keep calling it t-table, to get these points. So at any rate, t equals negative 2. So negative 2 plus 3 is 1, negative 1 plus 3 is equal to 2, 0 plus 3 is equal to 3, 1 plus 3 is 4, and 2 plus 3 is equal to 5. It's going to be a little bit weird when you go to make this graph because, we're used to, when we pick some values and plug them into the equations, we're used to actually seeing these values in the graph. But this is an y coordinate system. There's no place here to display the value of t. So these values have now allowed us to find our x coordinates, and then, other than to use these to find y, we are going to ignore them when we go to make the graph. So here we've got negative, and then we're plugging in a negative 2 squared. Anytime you deal with even powers, be very, well, all the time really, but especially with even powers, be very careful when you plug in numbers to expressions, especially when those numbers are negative. Because negative 2 squared and negative 2 squared have very different answers, at least as far as the signs are concerned. This is 2 squared, and the answer would be negative 4. This is negative 2 squared, or negative 2 times negative 2, which is positive 4. So we're going to make sure that we use those parentheses. We're also going to make sure that we follow the order of operations, which is going to say, do your exponent before you multiply. Do not cancel out those negative signs. So negative 2 squared is 4, and now it's negative 4. We plug in negative 1. Negative 1 squared is 1, and now it's negative 1. Then we're going to plug in 0. 0 squared is 0, and now it's still 0. Plug in the value of 1. 1 squared is 1. Now with the negative outside, it's again negative 1. 2. 2 squared is 4. Negative, so now it's negative 4. So our points are 1, negative 4. 2, negative 1. 3, 0. 4, negative 1. And 5, negative 4. Now, I'm going to pay attention to have some arrows on my graph indicating the direction of motion, not just the final path that the object took, described by these parametric equations. So from low to high, from my low t value to my increasing values of t, I'm going to graph these points in order, like you would normally do with a t-table anyway, but just stressing the fact that we're going to do the increasing values of t and mark that motion. So we have 1, negative 4. So over 1 and down 4. 1, 2, 3, 4. That's my first point. Then I'm going to go to 2, negative 1. And so I just went from this point to this point. So I'm going to put a little 1 here, a little 2 here, because I don't know what the final graph is going to look like, but I want to track the order here. We have 3, 0. Not required, but I'm going to, just for my own personal notes, add a little 3 in there. My fourth point is going to be 4, negative 1, so over 4 and down 1. And then finally, 5, negative 4. So over 5, 1, 2, 3, 4, 5, and down 4. 1, 2, 3, 4. And that was my fifth point. So I've got, indeed, a downward opening parabola. This was my first point, and I moved in this direction. This was the direction of motion. Now it's a parabola, so you can see I kind of made a little extension on my line, and I'm really tempted to just put a couple of arrows at the end of my graph to show that the graph is going continuously, or from negative infinity to positive infinity. But it's stated that I have a restricted interval for t. It's for values between negative 2 and positive 2. So it is important, because of this restriction, that I put some solid dots at the end of this parabola. If it was just less than 2, and if t was greater than negative 2 and less than t, then these dots would need to be open. And finally, in my last example, for a variation of this problem, if t went from negative infinity to positive infinity, well then it would be acceptable or required for me to put some arrows at the end of this graph. Now, I'm not going to just go boom, boom. I'm not going to put an arrow going down to the left, because the motion, as you can see, is coming up from the left, peaking at 3, 0, and then falling. So if I were to put an arrow at this, your teacher could very well have an issue with that, and say, well, are you indicating the direction is going down to the left? So let's just kind of just put some arrows as the graph comes up from the bottom left side of the graph to 3, 0, and then back to, well, as x increases to infinity, the y values are going to go to decrease to negative infinity. So here we go. A couple of variations on the restriction of the interval of t. And ultimately we had a downward opening parabola. Woo! Next example. our next example has some trig functions in them. So we have t ranging between, or time within the interval of 0 to 2 pi. That's probably because the period of sine and cosine, the generic period of sine and cosine is 2 pi. So if we let this move beyond 2 pi, it's probably just going to start cycling over itself and give you the same points again anyway. Well, look at the x value. The x is going to be tracked by a function that includes sine. We're used to the sine values tracking vertical movement on the unit circle. And the y has the cosine function in it. And on the unit circle anyway, the cosine function is related to x. So we have a little bit of backwards stuff going on here. So, let's see how funky the graph ends up looking. Now, I do, of course, have some idea of what this graph is going to look like, and you'll see how I know that from the next video that we do when we take these parametric equations and put them together into just the regular function form or rectangular form. But for now, you might need more points for this when you're doing this on your own, but I know what the graph is going to look like. Plus, I'm trying to do this in my head in front of the camera. So I'm going to just pick the easy values around the first rotation of the unit circle. Is that right? No, for you, 0 is over here. So I'm going to do the first, just one rotation around the unit circle, and I'm going to pick the easy points around that unit circle, the quadrantal points for sine and cosine. So we're going to do 0, pi over 2, pi, 3 pi over 2, and 2 pi. So let's put the 0 in. The sine of 0, remember sine on the unit circle, right? I'm not talking about, when I say x and y, I'm not talking about on a graph. On the unit circle, sine is y over r. So at 0 radians, sine is 0, and 0 times 4 is 0. At pi over 2, the sine of pi over 2 is 1. Now it's times 4. At pi, the sine of pi is again 0, times 4 is again 0. At 3 pi over 2, at 1, 2, 3 pi over 2, or 3 rotations of 90 degrees, sine is -1, and -1 times 4 is -4. And then a full rotation of 2 pi takes you to a sine value, again, of 0. For my y-coordinates, we've got -3 cosine x. So again, t equals 0. The cosine of 0 is 1. 1 times -3 is -3. At pi over 2, the cosine value is 0. So that's going to be 0. At pi, at 180 degrees, or pi radians, cosine is -1 times -3 is 3. And then we're going to get 0 and -3 again. So our points are 0, -3, 4, 0, 0, 3, -4, 0, and finally 0, -3. So we're going to plot the points, and again, I'm going to just make a little note as to where I'm putting the points, the order that I'm putting them, so I can put the arrows in the proper order when I'm done. So my first point is 0, -3. So that was point number 1. Then we're at 4, 0. That was point number 2. At 0, 3. So 0, 3. Third point, -4, 0. That was my fourth point, and then I landed back to 0, -3. Now again, this is only 4 points, and this is a smooth curve. So if you have no idea what this really should look like yet, then you might want to add some more in. Maybe pi over 4 and 3 pi over 4. Add some more angles off the unit circle, or they don't need to be, but why not use something you're familiar with to fill in the gaps. But what's going to happen is your graph is going to be a horizontal ellipse. And there is a way to understand that that's going to occur, that's the way it's going to look, and we'll talk about that in our next video when we go from parametric form into rectangular form. Now as far as my arrows, this is my first point, this is my second, third, and fourth, so as t equals 0, t equals 1, t equals, 0, pi over 2, pi, 3 pi over 2, and then 2 pi. This is my direction of rotation. Okay, so let's do another variation of this problem when we have a different restriction on the time period. what if it was only between 0 and pi? That would cut off this part of my t-table. Now really 3 points are probably really not enough. But if I take out the values, any values bigger than pi, then, well, I had 0, -3, 4, 0, and 0, 0, +3. So that was going from my first point to my second point to my third point. So this restriction on t would eliminate this portion of the graph. My direction would start from the bottom of the y-axis and rotate up, but if I don't allow the use of pi, then I need to have an open dot at the end of this graph, and that is the end of your second example. Our third example has an absolute value function in it. So we have t ranging from -infinity to +infinity, so there's going to be no end to this graph. X does have an absolute value function in it, and y is a linear function. Now, absolute value functions generally will have some kind of sharp bend in them. We're used to them being a V shape, either opening up or down, because generally our equations in Algebra 2, and even leading into pre-calculus, are y in terms of x. And if the absolute value function is wrapped around the x, you're going to have a parabola opening, a V shape opening either up or down. So we're going to have to pick some values of t to plug into these equations to see what the graph looks like. And something special happens with the absolute value functions when you get to negative numbers. It makes them positive. Absolute value will tell you how far a value is away from the, let's say, 0 on the number line, if you will, or distance from origin. Well, no. Let's go back to the number line. Absolute values tells you how far a number is away from 0 on the number line. So something is going to happen here where this expression equals 0. If you plug anything in that makes this negative, the absolute value is going to eliminate the negative sign, and anything that will allow this expression to be positive is going to keep everything sort of the same. You know, the absolute value 4 is going to be 4, nothing changes. But something happens when this becomes 0. That's the break. So we're going to make our middle t value equal to 3, and then pick a couple of numbers that are smaller and a couple of numbers that are bigger, and allow that to set up our table. Okay, so we're going to plug in 1. So 1 minus 3 is equal to -2. -2, the absolute value of -2 is +2, plus 1 is equal to 3. Put in 2. 2 minus 3 is -1. The absolute value of -1 is 1, and 1 plus 1 is equal to 2. For 3, we plug in 3. 3 minus 3 is 0. Absolute value of 0 is 0, plus 1 is 1. And now 4, well, 4 minus 3 is 1. The absolute value of 1 is 1, plus 1 is 2. So my x values are repeating. I'm not used to seeing that in a t-table. Plug in 5. 5 minus 3 is 2. Absolute value of 2 is 2. Plus 1 is, again, equal to 3. It almost... I wonder what that V shape is going to look like. Now, y is equal to t. So y is 1, 2, 3, 4, and 5. And our coordinates are, just to finish it up, 3, 1, 2, 2, 1, 3, 2, 4, and 3, 5. And if you know anything about the difference between relations and functions, you have an x value with 2 different y values. So this is going to be a relation. When you have a single x with more than one y value, in this case 2, that's a relation. So this is not a function. My points are 3, 1. That was my first point. Then 2, 2. That was my second. Just my own personal note here. 1, 3. That was my third point. 2, 4. That was my fourth point. And then finally 3, 5, which is here, and that's my last point. So, I think I graphed something wrong. Yes, I have that 3 negative one. It's right here. Okay, so I went from this point to this point to this point, and then we're going off forever. So the graph goes off indefinitely, and remember we came up from the bottom, so our arrows indicating the direction. When a weird turn on a, when you're thinking about graphing lines on an XY coordinate system, the direction is actually coming from right to left until we get to this point of 1, 3, and then it turns and goes off this way. So that is actually, look, so you still have the sharp bend from the absolute value function, and you're only getting a straight V shape because the function inside the absolute value is linear. You will get to some more sophisticated graphs with absolute values that don't just have a straight V shape. It's just because it's a linear function inside, by the way. And it is opening sideways. Now I just got reminded, since I thought, hey, let's point out the fact that this is a relation and just make sure that it hasn't been forever since you talked about domain and range. And in pre-calculus we use interval notation. So that's how I'm going to give my answers. The domain for this graph, let's do it in green. The domain is, what x values does this graph take on? It takes on everything from the x value of 1 and then goes to the right forever. So it goes from 1 to infinity. And we always use round parentheses to indicate there's no absolute value of infinity. And we're going to use a square bracket because the graph actually does use the value of 1. Well, in the graph, it uses the value of 1. And then the range, well, the graph goes up and down forever. And we're indicated that t goes from negative infinity to positive infinity. So it is going up and down forever. So the range is all real numbers, or goes from negative infinity to positive infinity. We've got one more example. This last example is admittedly a pretty tough one, at least in terms of, well, it's only tough in the sense that it's going to take a lot of points to be able to get an accurate graph of what you're looking at. You've got secant and tangent functions, and that's going to create, not that you know how to find this yet, but it's going to create a hyperbola opening up. So you're going to deal with, you don't have to find the asymptotes, but it's going to have undefined values. It's going to have some kind of like weird shape with the asymptotes and some empty space in the middle. So just doing a handful of points like the quadrantal points, 0, pi over 2 pi, 3 pi over 2, and 2 pi, is not going to be sufficient to give you a complete picture of what this looks like. So I'm going to go ahead and pause the tape or video, and that'll give you a chance to, really work out a good length up to this t-table and get a good number of points to see what this thing actually looks like. And then again, please watch my second video, because really, I would suggest to graph this one, you always want to do parametric equations, graphing them off of a t-table like this to get that direction of motion. But this would actually be easier to, ultimately know what the graph is going to look like by getting this into rectangular function or regular function notation. And actually that's kind of true with all parametric equations, but especially this one because of the nature of what this graph is going to look like. So make out a t-table, get yourself a nice number of points. I'm going to pause it, fill up the table, and then draw you a picture. And then make sure you watch the next video where I take most of these examples and put them together into regular function form or rectangular form, where we eliminate the parameter of t. So, here is our table. Clearly needed the aid of a calculator with some of these questions, and you'll notice that some of our points came out to be undefined. Well, even though I'm using my, I use my calculator because I got decimals, right? I didn't do this in my head. But I do have all these numbers off of the unit circle. That's just out of habit. Because, every time I think of a trig function, sine, cosine, secant, cosecant, I go right back to that unit function, or unit circle, that I learned not very long ago with all those points. And let's not forget that secant is r over x, and tangent on the unit circle is y over x. So these two functions are going to be undefined at any point of rotation where the x value is equal to 0. So at pi over 2, where my x value is 0, or 3 pi over 2, where again my x value is going to be 0, the secant and the tangent functions are both going to be undefined at the same time, and so thus we have some holes in our table. So, excuse me, allergy season when I'm making these recordings. Sorry for all the coughing and swallowing. Okay, so we have 1, 1, and that's going to be our first point. We have 2.2 and 3, so a little bit past 2 and up to 3. That's the second point that I'm graphing. We have negative 6, negative 1, or negative 6.24, so 1, 2, 3, 4, 5, 6. A little bit past and down to negative 1. And that was the third point that I plotted. We're at negative 5, 1. So 1, 2, 3, 4, 5, 1. That was the fourth point that I plotted. Negative 6.2 and 3. So negative 6.2 and 3. That's the fifth point that I plotted. Skip 2.2 and negative 1. So 2.2 and negative 1. And that was the sixth point that I plotted. And then finally at 1, 1, which we're right back to where we started from. So this is a case where it's really, really good idea that I numbered these. We got this side is a hyperbola, so we're coming through these points, and there are asymptotes here, and I didn't get infinitely close to 0 or infinitely close to 2 pi, so just the fact that these are my points, my 3 points, the graph isn't really stopping there. I just did not allow myself to get infinitely close to these values and really work on those asymptote values, so they do go on forever. So 3, 4, 5. So my motion is coming up this way. And then over here we have 1 and 2, and then this 6. But because of the weirdness of the asymptotes, this isn't going to come up here and approach. There's an asymptote that we don't see that's here. And the graph is coming up here, and it's coming up to the bottom of this asymptote. And when it gets over that undefined value, to the other side of that asymptote, it's actually going to come back over here and swing through these points. So the graph on this side is coming up through this direction. And I think I just got a little bit out of balance there. It's not really supposed to be going up that sharply. But I think you get the point, right? We have these hyperbolas, this horizontal opening hyperbola, and I actually missed the center too, because look, if I have this at negative 5 and at 1, and if I come in 1, 2, 3 units, really I kind of missed the center as well. This is the center of the hyperbola right there at negative 2, 1. And we'll understand how to find that center actually in the next video, again, where we put these parametric functions together into rectangular form. I'm Mr. True. Go do your homework. Almost done. I was starting to do with the asymptotes that we have here with the hyperbola, starting to question if I had forgotten something as I was setting up this example for you, and I did. The example that I used to inspire this, that I made for you, for this secant and tangent relationship where there was a hyperbola that you were forming, they had restrictions on t going from negative infinity to positive infinity, basically saying there was no restrictions allowing that graph to go off indefinitely, becoming closer and closer, infinitely close to those asymptotes. So just a little fix on my restricted domain here, my restricted interval for t. There wasn't one. So now, one more time, bam, go do your homework.